Many people imagine black holes as the ultimate cosmic vacuum cleaners. We see them as dense, hungry traps where even light finds itself shredded and consumed. We need a more accurate definition. A black hole is not a hole in space. It is a region where the cost of return becomes impossible. General relativity describes this as the ultimate expression of gravity. When mass and energy are packed tight enough, they curve spacetime so severely that they create a boundary known as the event horizon. This horizon acts as a causal boundary. Outside, paths still lead away. Inside, however, geometry shifts so every possible future points downward. The event horizon isn't where gravity becomes magical. It is where escape stops being part of the geometry. Ultimately, general relativity proves that the black hole erases the spatial directions required to leave, moving past the common idea that it physically sucks matter inward. General Emergence Mechanics, or GEM, builds on this by asking what kinds of geometry can remain coherent under such extreme constraints. In this framework, gravity acts as a depth gradient. Matter creates a landscape of persistence basins, and a black hole represents the extreme limit, a basin so deep that the exit route physically ceases to exist. This distinguishes the two sides of the horizon. Outside a black hole, escape is expensive. Inside a black hole, escape is no longer admissible. GEM calls this an admissibility boundary. It acts as a hard filter, separating what is possible in our reality from what is physically forbidden. Rather than the laws of physics turning off, the universe simply edits the menu of available futures. The horizon is the line where return falls out of the menu of reality. Crossing into the hole isn't a collision with a wall, it is the geometric revocation of the ability to go back. Deeper in, local geometry becomes harder to route through. Light cones tilt inward, pointing exclusively toward the center. GEM calls this terminal vacuum viscosity, a state where the vacuum refuses an outward route, geometrically locking all futures inward. A black hole is where the vacuum stops being a road and becomes a one-way funnel. At the very bottom of this funnel lies the singularity. Standard models call this an infinitely dense point where physics breaks, though most experts expect quantum gravity will eventually provide a clearer picture. GEM suggests a more cautious interpretation. The singularity may not be a place. It may be the failure of our current admissible description. In this view, we aren't traveling toward a point of physical destruction, but toward the absolute limit where our geometric map of reality stops functioning. This limit leads to the information paradox. What happens to the descriptive data of the matter that falls in? Within GEM, we define information as coherent structure, the specific arrangement that makes an object what it is. This reframes the entire problem as a question of survival. The black hole information problem is really a persistence question. Can coherence be hidden, transformed, or preserved when escape is no longer admissible? We know black holes aren't perfectly eternal. Quantum field theory tells us they slowly leak mass over trillions of years through Hawking radiation, a complex interaction between the horizon and the vacuum. It suggests that even the darkest basin may have a boundary cost. If black holes eventually evaporate, it proves that even the most absolute geometric boundaries must eventually pay an energetic toll to the rest of the universe. This principle of persistence, the ability of a structure to maintain itself against disruption, connects the black hole to the rest of nature. From the bonds of a molecule to the quadients of a cell or the patterns of a civilization, everything exists only as long as it can pay the coherence budget required to hold its form. We see this most clearly at the horizon. A black hole does not pull like a mouth. It edits the map of possible futures. The event horizon is the universe's most dramatic persistence boundary. While general relativity remains our proven theory of spacetime, GEM provides the visual language for how return geometry collapses at the limit. Think of it as a strict boundary dictating what can come back, leaving behind the older imagery of holes or vacuum cleaners. A black hole is not where reality becomes nonsense. It is where geometry becomes absolute. Outside, the universe still offers choices. Inside, the future has only one direction. Is a black hole a place where physics breaks, or where geometry becomes too expensive to escape? Ultimately, the nature of reality depends on both the matter it contains and the physical and energetic costs required to navigate its futures.